Hi there, guys. It's just me, Mr. Wee, again. So this is part two of number 17 of the month 5 test corrections. Um, so let's kind of go over what happened from having this, the rate of change, is equal to k times p, and how it got to here, which is our final result, where you take the initial population. So we had it right here. I'm sorry. So that's like a capital P. The initial population there times k is basically equivalent to the rate of change, and how we got to here, which is the rate of change, to how the population has changed. So if you think about it, it's e to the k to the t. This is the rate of change. So I've been kind of saying this a little bit wrong, but this is the rate of change. This is the rate of change. So this is the rate of change. And then this is actually how it changes, how things change, how, just how it changes, how things change. So again, rate of change is sort of like the change over time, right? Okay, how your population changes over time. This just tells me just change, how things change. That's it. There is no change over time. So basically, this is the rate of change. This is just how things changes. The derivative of this will be this. But how do we get from here to here? So let's just start with this, and let's take the antiderivative. Well, if you think about it, you actually have two variables going on here. You have the population and you have time. So what we're going to do is this becomes a separation of variables problem. So if you think about it, I'm going to divide this by p. So I have dp over p, and I'm going to multiply both sides by dt, and I will get k times dt. So again, what I just did is I divided both sides by p, so the p's will cross out here, and I'll have dp divided by p. But then dt, I'm going to multiply both sides by dt to get rid of the dt here, and I have dp over p, which is all a separation of variables. This is a separation of the p variable, and dt I left completely by itself. At this point, I take the integral of this. And if you don't see it, this is what I have. The integral of 1 over p, if I rewrite this as 1 over p with respect to p, is equal to the derivative of k, which is just a constant value, of dt. The derivative of this would be ln of p plus c, there's a constant c, is equal to k times t. If you think about it, this is just like a, just think of this as a constant, like 3. Okay, the antiderivative of 3, right, or a constant, the constant 3 with respect to t would be 3t, but here it's k, so it's kt plus c. Okay, that's not so bad. And then if you think about it, this is some constant that is not the same as this constant, but I'll subtract whatever constant this is from both sides. And remember, this constant on the right-hand side is not equal to the constant on the left-hand side. We don't know that. So if I subtract, I at least subtract this constant away, and I subtract that same value here from here, I'll get some other constant. I don't know what that value is. It could be any value. I just know that this constant minus whatever the heck this constant was from this side is equal to some new constant. I don't know. So I have ln of p is now equal to, let's see, did I do that right? Yeah, I did. ln of p is equal to kt plus c. And then what I'm going to do now is I want to get rid of that ln. And how do I do that? I put all of this as a power to base e. Whatever I do to one side, I got to do the other side. So this all becomes an exponent. And here's what I got so far. This will cancel out. It's starting to look a lot like, see, I got p by itself, starting to look a lot like what we have here. From here to p is equal to something. How did I get to that, though? I don't know. So here, what I have now is I got e to kt. And if you know your exponential property, this plus c will kind of be like times e times c, okay? And then I'll have p is equal to, let's see, This is, again, e to the c is just another giant constant, c. The only difference is someone found out that that c, with that giant c, that giant constant, e to the c is basically another giant constant. If we put it back in the front, if you look at this and you look at this is a review from what we went over in class a while ago, but maybe you don't remember. This is just a proof, right? We don't have to memorize proofs. But to get from here to here, basically that giant c, p is equal to c times e to the kt, and over up here is is equal to p0 times e to the kt. Uh-oh, they both look very similar. The only difference is that giant c, what we found out is this. Let me back up. Sorry, it's not as easy writing as you guys think with this camera. It's a nice camera, but it's a bit hard to work. This is the initial population, or whatever this is, the initial value of whatever you're dealing with. This is the initial population. So if we write that one more time to make it look a little bit nicer, someone found out that by doing this, simply saying that your new population, that giant C, now becomes the initial population, p to the 0 times e to the kt. So this is a proof. This is how we got from our initial statement here, dp over dt is kp, to get from here to here. Okay? All right, guys, that's all I have for you guys for the proof. Thank you.